All right, so let us get started with today's lecture. So in last lecture, what we did was we looked at dataset loading and dataset pre-processing, especially with respect to tokenization and input-output pairs. Today, for the entire lecture, we are going to spend on part number 3, which is assembling the model architecture. So think of this lecture as creating the brain of the small language model really. I plan to keep this lecture very intuitive and mathematical, and then towards the end, we'll also go through the code file. Before we get started, let me give you a quick recap of what all we have seen so far. We started with this tiny stories data set essentially, and the tiny stories data set looks something like this. Yeah, so this is the Hugging Face website on which we downloaded the tiny stories dataset from. It's a dataset of 2 million stories. And what we decided to do was we want to construct a language model which has around 10 million to 100 million parameters. And we want to pre-train this language model on the tiny stories dataset. This is a very specific dataset since it consists of stories which 3 to 4 year old kids can really understand. And that's what makes it a small language model. We looked at the fact that small language model has two major things. The first is that the number of parameters should be way lesser than billions and billions of parameters. That's number one. But the second most important thing is that it should be trained on a very specific data set. The aim of our workshop is that towards the end, we want to be able to generate sentences which look like English language. So basically coherent English sentences. And for that, the model will have to learn the two things. The model will have to learn the form of the language and the meaning of the language. And the way we are going to train this model is for the next token prediction task. And the beautiful thing about language models, as we saw in the previous lecture, is that although they are only trained on the next token prediction task, they develop this ability to uncover the form and meaning of language more like a byproduct. So if we actually are able to generate coherent sentences with a model with only these many number of parameters, it will be an amazing thing for us to do. And the same code file which we started with yesterday can be used later on by all of you to build small language models on your specific data sets. So we loaded the data set earlier. That's the first step. If you take a look at the code which we saw, the first step is to load the data set from Hugging Face. That's the first thing we did. And then we did data pre-processing. This is extremely important. We saw two parts in the data pre-processing pipeline. The first step is related to tokenization. And within tokenization, we saw three types of tokenization. If you remember, we saw word-based tokenization, we saw character-based tokenization, and we saw subword-based tokenization. Both word-based and character-based tokenization have some issues or limitations, and subword-based tokenization solves both of those issues. One such subword-based tokenization scheme is the byte pair encoder, which we used to tokenize our text. So we took all of our stories and we converted them into a bunch of tokens, and they were assigned token IDs. However, they assigned token IDs, we maintained a list of vocabulary. We maintain a vocabulary. And remember, in subword tokenization, the vocabulary consists of characters, words, as well as subwords. And then every subword or every character is assigned a token ID. That's called tokenization. That's the first step. The second step is that tokenization is not enough. We need to very strategically store the token IDs onto our disk. So for that, we took all the tokens. So imagine a bag in which all of the stories or the tokens are dumped into, and then we split the bag of words or bag of tokens into batches, and then we write each batch onto the disk. That's how we create two files. We create a train.bin file and we create a validation.bin file. And each file has a huge number of token IDs. On an average, the train.bin file would have 100 million token IDs, and the validation.bin, which we loaded specifically, would have around 1 million token IDs. And in which part of the code did we do this step? It's in step number 2. So if you look at the code over here for step number 2, there are two things which are happening here. There is the tokenization which is happening here. We are using the byte pair encoder from GPT-2. And the second step here is that we are writing all of the token IDs onto the disk. So until or after this step is finished, we have two files. We have train.bin file and we have validation.bin. So all of you who ran this code with me yesterday, you would have seen that this process is extremely time consuming. And if you did not do this memory mapping, which means that if you don't store the file on disk and if you store it on memory, it will take even more time. The third step, which we covered towards the end of the class, was probably the most important step in yesterday's lecture because it actually showed the path towards the next token prediction pipeline. And here we actually created input and target pairs. I want all of you to remember how we created input and target pairs, right? We decided two things. We decided the context size and we decided the batch size. Okay. So if you take a look at the code very specifically, to create the input and target pairs, what is being called as block size over here, that's the context size, and what is being called as batch size over here is the batch size. These are the two variables which we need when we create the input and the target pairs. And when we call this function, a batch will be created of input and target. We have not called this function yet, so we have not yet defined the block size and batch size, but we will do it when we start building the training pipeline in day 3 of this workshop. All right, and the way input and target pairs are created is as follows. Once you define a context size, let's say the context size is equal to 4 in our specific case, then what you do is that if the context size is 4, you take an input with 4 tokens. That's my, so these are the input token IDs, which I'm marking here in the green color right now. And then you shift the input to the right-hand side by 1. And that's my corresponding output token IDs. So one day a little, the 4 token IDs corresponding to this, that's the input. And day a little girl, that's the output, which I've shown here also. One day a little and day a little girl, that is the first input output pair. And although it looks like one input output pair, there are 4 prediction tasks which are happening here. So for one day should be the output. For one day as the input, a should be the output. For one day a as the input, little should be the output. And for one day a little as the input, girl should be the output. That's why it's called as the next token prediction task. Eventually, we'll make our model so good that it predicts these next tokens perfectly. And so this is the ground truth. What our model predicts might be something completely random initially. Our whole aim is to match the model prediction with the ground truth prediction. And currently, I just showed you one input output pair, right? In a batch, there may be multiple input output pairs. So here, the number of rows x1, x2, x3, x4, y1, y2, y3, y4. That's a batch, which has 4 input and output pairs. So today's lecture is going to start at this exact same point where we have the input and the output pairs ready. And now we are going to assemble the architecture. Is this clear until this point for everyone? Can you mention in the chat? Okay, we have been through this in detail in yesterday's class also. So now without wasting any more time, let's actually get started with today's lecture. If it's not clear to you, I would encourage you to go back through the recording of the previous class. Now remember that the recording of the previous class is uploaded on the dashboard. So all of you should be able to see the recording. For the people enrolled in the pro plan, the lecture notes have also been uploaded. So today's lecture begins at this point, and let me set up the context for today's lecture. So let's say we have the input tokens, right? One day a little. These are the input tokens. These input tokens are going to go through some pipeline, which I've mentioned with a question mark here. We don't know what that is. And then 4 next tokens are going to come out. So the language model is going to predict 4 next tokens, which are going to be matched with the ground truth. So let's say one day a little, right? We know the ground truth. For one as the input, day should be the output. For one day as the input, a should be the output. For one day a as the input, little should be the output. And for one day a little as the input, girl should be the output. This is the ground truth. But when these 4 tokens pass through the language model, we'll get a set of predictions, which are 4 tokens, which earlier won't look like the ground truth. Today, our task is to understand how do we get the prediction of the next 4 tokens. So what happens to these input tokens, this question mark, what exactly happens through these input tokens, and we get these 4 predictions. What is going to happen in the next lecture is that once we get the 4 predictions, we are just going to define the loss function, and then we are going to do the back propagation. And then we are going to set the training pipeline. But today we are going to think of this forward pass, which essentially means that how exactly are these 4 tokens going to be processed to predict the next 4 tokens. Okay. I hope the context for today's lecture is clear. Our whole lecture is going to operate in this context. So in the middle of the lecture, if you feel confused that what is exactly going on, just come back to the start where I've set up the context here. We want to understand what this question mark is. What happens through these 4 tokens? And what happens to these 4 tokens is called as the language model architecture, which I've also called as the small language model architecture over here. Essentially, these tokens go through a journey. This journey is described with this schematic, which I've shown on the screen right now. And if you look at this schematic, this question mark is essentially this whole schematic. And right now it must be confusing to all of you to see what exactly is this schematic, but I'm going to break it down so that you understand each and every component of this architecture. So first of all, this architecture is divided into 3 blocks, which I'm marking with the yellow color right now. The first block is called as the data input, or very simply, let me call it the input block. The second block is called as the processor, and the third block is called as the output block. Now the input, so you see here the input text for the LLM, this is where these 4 tokens are going to go. And then they are going to go through this entire journey from the input block to the processor block to the output block. And then when we are going to come out of the output block, we'll have the predicted 4 next tokens. So it is our responsibility in this class to understand the journey which these input tokens go through. And I'm going to start this journey by explaining regarding the input block first. All of these blocks are equally important to understand. And we are initially going to start by understanding the input block. All of you must have heard of this paper, Attention is All You Need, right? And it's frequently used in context with language modeling. How many of you have heard about this paper or read about this? Yeah, this paper is extremely famous. I'm sure many of you must have heard about this paper. If you have not heard about this, it's essentially this one. This is the paper which led to the revolution in language modeling, and I'm pasting the link in the chat. And so what's the link between this and the architecture? Well, the multi-head attention which you see over here, that essentially comes from this transformer or the attention is all you need paper. So when we look at the processor block, we are going to understand attention also. But first, it's important to understand the input block. Now, the thing is, most of the people really only focus on the processor block because the processor block is very cool and there are so many different and new things which are happening in the processor block, right? But if the input block is not efficient, nothing else will be efficient. And as a person who wants to build an SLM from scratch, you need to pay equal attention to all of these 3 blocks. So if you take a closer look at the input block, we have already implemented one step out of this input block. If you see, we have already tokenized the text through a subword based tokenization scheme. So these numbers which have come over here are essentially token IDs, right? Which are based on my vocabulary. So we have already performed tokenization step. The next step is extremely crucial, and that's the step of token embeddings. Token embeddings is the whole idea that words can be represented as vectors. The idea of token embedding is words can be represented as vectors. And if this is the first time which you're hearing about this, it's actually an incredible concept. Or people who know about this, for you now, it must be intuitive and straightforward. But for people who are learning about the language model architecture for the first time, this might come as a shock to you. But the first invention for this happened in the year 2014 when Google came up with this algorithm called word2vec. And the whole idea here was that computers can't really understand numbers, can't really understand text, right? So we convert it into numbers. So you might say that token IDs are already numbers. But the issue with token IDs is that they don't encode any meaning at all. They don't encode any meaning. The idea with token embeddings is that words will be represented as vectors and words which are similar in meaning will have vectors which are closer to each other in the vector space. So for example, if you take a look at cat, right, and if you take a look at kitten, both of these are really, it's the same meaning. But if you just encode them as token IDs, the semantic layer or the meaning will be completely lost. The idea of vectors is that if I can represent words as high dimensional vectors, and somehow if I train these vectors to capture the meaning, that would be really awesome. So that's what Google showed in the 2014 paper. They showed that if you take a huge bunch of words, you can really train a neural network to convert words into vectors. And these vectors are such that similar meaning vectors will lie closer to each other in space. So if you take a look at this, here I have represented every word as a vector, right? And if you see meaning, words which have similar meanings are closer to each other. So these dark red words such as battery, charger, tool, etc., they are closer to each other in the vector space. If you take a look at refrigerator, oven, microwave, etc., they are closer to each other in the vector space. So this is one of the most fundamental breakthroughs to build language models. This idea that words should be represented as vectors and their meaning should be captured. Uh, the words which lie or the words which have similar meaning will lie closer to each other in vector space. Uh, and I really want all of you to think how non-intuitive this is. Who would have thought that a word can be represented as a vector and that too, vectors of similar words will lie closer to each other. So here is a blog which has been written by one of our live class students, Mayank, and is one of the best blogs on word embeddings. So just take a look at this video here for once. The whole idea is that when words are represented as vectors and eventually trained, words which mean similar will lie closer to each other in vector space. So then naturally your question would be that how are we going to train these vectors? And currently, when we assign vectors to each of these token IDs, we are going to assign them randomly. We are going to train them along with all the other parameters of this language modeling architecture. So actually what's going to happen is that, let's say there is this vocabulary, right? There is this vocabulary of words and let's say that has 1, 2, 50257 token IDs. What I'm going to do is that I'm going to randomly assign each token ID to a higher dimensional vector. Let's say the token ID number 1 is a 768 dimensional vector. The token ID number 2 is a 768 dimensional vector. The token ID number 50257 is also a 768 dimensional vector. I'm going to assign random values initially. So these vectors are going to be initialized randomly. And this gives rise to something which is called as the token embedding matrix. This gives rise to something which is called as the token embedding matrix. And the token embedding matrix in this particular case has number of rows equal to 50257 and the token embedding matrix has number of columns 768. So I'm mimicking GPT-2 architecture a bit over here. That's why I'm choosing these values. These values need to be very specifically chosen. But for now, let's assume these are the values. And why 50257? So imagine this as the rows, right? So row number 1, row number 2, these are all my token IDs which are there in the vocabulary. So the way it happens is that you first have a huge data set and you apply the byte pair encoding algorithm to this data set. The byte and this data set is not the tiny stories data set. This might be the whole data set in the English language, etc. Or if you want to build a multi-language tokenizer, it will be a data set in multiple languages. You take this data set, you apply the byte pair encoding algorithm, and then you come up with the vocabulary. You come up with the vocabulary of the subwords, and you assign token IDs to each subword. That's why there are 50257. And then each of these 50257 IDs in the vocabulary will be associated with a 768 dimensional vector. Our hope is that once the language model is trained, all of these parameters also will be trained so that vectors of similar words will lie closer to each other. So all of you would be thinking that, or many of you actually asked yesterday that these 175 billion parameters, where do they come from? In today's lecture, I'm going to show you exactly where all these parameters come from. And this is the first place where these trainable parameters come from. All of these values over here, right? All of these 50257 multiplied by 768 values here, these are trainable parameters. So henceforth in this lecture, whatever I'm marking as P in a violet color, that's going to be trainable parameters. If I forget to do this, please remind me. So the first place where I've marked it as P is because this is the first place where trainable parameters arise. We don't know these values from the start. We are going to initialize them randomly. And if you see here itself, we have how many training parameters? 50257, 50257 multiplied by 768, right? This is it's even difficult to count. It's 38, around 30 million parameters. So we have around 30 million parameters. Let me ask in millions. Yeah, so here itself we have around 30 million parameters, right? So let's keep a track of the different number of parameters as they are assembled. So we have 38 million parameters here. So remember how important there are the two variables are. The first is that the embedding size, as you increase the embedding size, the number of parameters increase by a lot. And the second important variable is the vocabulary size. And you have to define the vocabulary size when you create the byte pair encoding. It's a hyperparameter which you have to define. For example, GPT-4 had around 100,000 vocabulary size. GPT-2 has 50257. If you are doing a multi-language tokenizer, you have to have more vocabulary size. But more the vocabulary size, as I showed you over here, more are the number of trainable parameters, right? And vocabulary size. So the general formula for the number of trainable parameters in the token embedding matrix is vocabulary size multiplied by the embedding dimension. That's going to be the general formula over here. These are the number of trainable parameters which I have right here. Now remember here that there are two things which are happening. We are going to pre-train a small language model in this workshop. I'm not teaching you how to build a byte pair encoder from scratch. That's a completely separate thing. Building a byte pair encoder from scratch requires a different data set. We are not talking about this step right now. We are assuming that we already have a vocabulary of 50257 tokens. But keep in mind that here also there is a lot of scope for doing research. The way you define tokenizers, which algorithm should be used to get these tokens, etc. Because as I showed you yesterday, the quality of tokens also affects how your model becomes. GPT-2 was not very good at dealing with Python code because its tokenizer treated indentations not very nicely, unfortunately. So that's the first step over here. We had these token IDs and we converted the token IDs into token embeddings. There is a second step which we are going to learn about right now, and that's something which is called as position embeddings. So why are we even talking about position embeddings? The reason is because, uh, let's say, if I say the dog chased the car, it could not catch it. Let's say if this is my sentence, right? And we only go ahead with word embeddings. Now this it and this it, they clearly refer to different things, right? This it refers to the dog and this it refers to the cat. But word embeddings don't take into account position at all. If you just take into account the meanings of words, this it and this it means the same thing. So that's not good for us. We need to take into account the position of different tokens as well. So here the dimensions of every token embedding vector was 768. Similarly, we are going to construct a position embedding matrix. Can someone tell me what will be the size of the position embedding matrix? I am going to explain this to you, don't worry. So the dimensions are 768, that's fine. So the number of columns are 768. What should be the number of rows in the position embedding matrix? Yeah, there are some people. So it's not actually same size as the token embedding matrix. How many positions do we have? How many positions can tokens take? What determines the number of positions? So it's not the vocab size. It's actually based on the context size. Because take a careful look over here. Remember, so here the context size was 4, right? So I can have a token in either position number 1, position number 2, position number 3, and position number 4. I can never have a token in position number 5 because that's not my context size. Essentially, the maximum value of the position is determined by the context size. And since we are going with GPT-2, the token embedding matrix will have a size of 1024, 1024 cross 768. This means that for every position, for position number 1, there will be a 768 dimensional vector. For position number 2, there will be a 768 dimensional vector. Similarly, for position number 768, there will be a 768 dimensional vector. Sorry, for position number 1024, there will be a 768 dimensional vector. So this is the position embedding matrix, right? Now, we have a token embedding matrix and we have a position embedding matrix. So let's see carefully how we can get the token embeddings and position embeddings. If we have these token IDs, let's say if I have these token IDs and I want to get the token embeddings of these token IDs and I want to get the position embeddings of these token IDs. So here the values which I'm using, don't pay too much attention to why I'm using these values. I'm trying to mimic the architecture of GPT-2 as much as possible. So these are the token IDs right now, right? How would you find the token embedding vector? So let's say for this, I want to first uh, not have token IDs over here. I want to convert each of these into token embedding vectors. So how do I do that? The way to do that is you look at the token embedding matrix. So I look at the token embedding matrix, which I just saw over here. And here it's 1, right? So I look at the first row and I get a 768 dimensional representation for this. So this is 768 dimensional now. Then what I do is the second token ID is in number 11, right? So I'm going to look at number 11 over here and I'm going to get the 768 dimensional vector. So I'll have the 768 dimensional vector over here. Then I'll look at row number 15 and get the 768 dimensional vector. And then I'll look at row number 24 and get the 768 dimensional vector. That's why we need to maintain a token embedding matrix. It just becomes very easy to look up a particular row and get the vector. How would you get the position embedding? How will you get the position vectors for each of them? So this one, it comes at position number 1, correct? So I'll look at the first row of the position embedding matrix and I'll get its 768 dimensional vector for position number 1. For the second token, it comes at position number 2. So I'll get a 768 dimensional vector for the second position. For the third token, it comes at position number 3. So I'll get a 768 dimensional vector here. And for the fourth token, we'll look at position number 4 over here. And hence we'll look at the fourth row of the position embedding matrix. And that's where we get a vector over here. So there are some questions in the chat regarding position embedding matrix, right? So let me try to explain it once more. Essentially, take a look at these token IDs. This is token ID number 1, ID number 11, 15, and 24, right? These token IDs, we got their token embedding vectors. We got their 768 dimensional token embedding vectors. That much is fine. But now we also want to encode information about the position of these tokens. How do we do that? We need to get some vector related to their positions as well. So for that purpose, we maintain a position embedding matrix, and the number of positions which any input can take will always range from 1 to the context size. Because as we have seen here, every input every input row which we have, the maximum number of columns which can be present in every row is constrained by the context size, which are how many number of tokens the LLM can look at once. So the positions which I need to convert into a vector are essentially only going to be from 1 to 1024, which is the context size I'm assuming in this particular case. I will never have a position number 1025 because that's going to go out of the context. So in this particular case, along with getting a token embedding vector and along with getting a position embedding vector for every position, I get a token embedding vector for every token and I get a position embedding vector for every token. And then what I'm going to do is that I am going to add the token embedding vector and the position embedding vector for every token. So I'm going to add the token embedding and the position embedding vector for each token. And since the size is going to be 768 itself, what I'll ultimately get is a token embedding vector plus a position embedding vector whose size is 168. So for every token ID now, I have a 768 dimensional vector, which is the summation of the token embedding vector and the position embedding vector. So each vector which is associated with every token ID is now a summation of my token embedding vector and my position embedding vector. So remember that the context size which I showed in this example is equal to 4, right? So if the context size was 4, the size of this table would be 4 multiplied by 768. But in real life situations like GPT-2, the context size is usually very large. That's around 1024. I think this will be much more clearer if I explain to you with another example. So stay with me for a moment over here and let's see what actually happens to every token now. So I've constructed this another example so as to explain to you three things: token IDs, token embedding, and position embeddings. So just try to follow along. If there is a sequence of input tokens such as this, a true friend accepts you. The first thing which is done is that every token is assigned to a token ID, right? Every token is assigned to a token ID. That's the first thing. So we maintain a vocabulary of words. And so let's say friend is a token here. That's assigned to a token ID from this vocabulary. That's the first step. So imagine this, if token you can consider as a student or a person, that token has got a badge now. That badge is equal to the token ID for that particular token, right? That's the first step. Then what is done is that every token is converted into a 768 or a high dimensional token embedding vector. You can think of this as the entrance exam for the student. So now a student has enrolled in a school and a student is a token. Every token gets a badge, similar to every student gets a roll number, right? That's the badge, which is the token ID. But that's not enough. Every student also needs to be assigned an entrance exam, which is basically our 768 dimensional vector. So imagine there are 768 questions. We don't know what these questions are because we are randomly assigning these values initially. So every token will now have 768 dimensional vector assigned to it. But the position is also important. So friend comes in position number 3. So it will also have a 768 dimensional position embedding vector associated with it. And then what we do is that for every token, we add its token embedding to the position embedding, and that gives rise to the input embedding. So if you look at one specific token, its token embedding is 768 dimensions, its position embedding is 768 dimensions, and the resulting, which is the token embedding plus position embedding, that's the input embedding. That's the 768 dimensional vector here. So if you now take a look at our 4 tokens over here, now we have converted them from token IDs into 768 dimensional vectors. So the way this X1 matrix will now look like is that it will have a 768 dimensional vector. It will have a 768 dimensional vector. It will have a 768 dimensional vector. And it will have a 768 dimensional vector. So the size of this X1 matrix will now become 4 multiplied by 768. Why 4 multiplied by 768? Because we have 4 token IDs and each token has a 768 dimensional vector. So remember why we are using this. We are just using the number 768 and 1024 as examples over here. So 768 is the embedding dimension, which is used as an example over here. In yesterday's case, this was equal to 4. And the context size which we are using today is 1024. That's also an example. In yesterday's case, we used it as 4 also, right? So the first step, what happens in the input block, actually, there are two things which are happening in the input block. Every token is converted. First, they are converted into token IDs. That's the first step. Every token is converted into, so we are looking at one input sequence at a time. In one input sequence, every token is converted into a token ID. Every token ID is converted into a token embedding, and then we add the positional embeddings. And that gives rise to something which is called as the input embedding. This input embedding is what goes into the processor block. So if you take a look at this part here, this is, I have tried to explain this in one more way over here. So let's say this is the 4 tokens we have chosen, right? One day, a little. Each token will be converted into its token embedding, right? Each token will also be converted into its position embedding. And then we add the token embedding and the position embeddings for these 4 tokens together. So for one day, a little, right? One is at position number 1, day is at position number 2, is at position number 3, little is at position number 4. So for one, we add the token embedding to the position embedding. That gives input embedding of size 768. For day, it's at position number 2. Token embedding plus position embedding gives me input embedding of size 768. Similarly for and little. So by the time we pass to the, by the time we go to the processor block, these 4 token IDs which are come in, right? These 4 token IDs which are come in, now each of this is a high dimensional vector. So the size of the matrix which passes into the processor block, that's actually 4 multiplied by 768. Is this clear to everyone? The first part, which is the processor block, it is the token embedding vector added to the position embedding vector, and it gives rise to the input embedding vector. Okay. Now, one more thing which I forgot to do here, and keep reminding me regarding this. Here I marked it as P, right? So these are trainable parameters in the token embedding matrix, which I'm marking as P right now. But we also have trainable parameters in the position embedding matrix, which is, if you're considering GPT-2, for example, if you're considering GPT-2, the vocabulary size is 50257. The embedding dimension is 768, and the context window is 1024, let's say. So the size of the token embedding matrix is around 38 million, which we just saw. These are trainable parameters given by vocabulary multiplied by the embedding dimension. And the size of the position embedding matrix is 768 multiplied by 1024, right? Which is the context window multiplied by the embedding dimension. Let's see how much that is. 768 multiplied by 1024. So this is around 0.7 million. So the size of the token embedding matrix, or the number of parameters in the token embedding matrix, are around 50 times larger than the number of parameters in the position embedding matrix. So if you add both of these together, until now, before we even reach the processor block, we have around 40 million trainable parameters right here. So before we reach the processor block itself, we have around 40 million trainable parameters. Context window and batch size are very different from each other. Context window, if you remember from yesterday what we have seen, context size is the number of columns, and context and batch size is the number of rows when we are looking at creating input and output pairs. So people are asking, like, where are these numbers coming from, right? Don't be confused by these numbers. These numbers 768, 1024, which I am taking, are specifically because when OpenAI released GPT-2, they had these numbers. That's why we are staying with these numbers. Okay. So now what we are going to do is that I'm going to now take you to a journey into the processor block. So now once the input block is clear, we are going to understand the processor block. So pay very careful attention here. And I'm going to take assistance of my schematic over here. Remember that what's the form of the input when we go to the processor block? Can someone tell me the dimensions of this input when we go to the processor block if you are following along? So someone is saying 1024 by 768. That's not the correct answer. 1024 is the context size, but currently we are looking at only four tokens, right? We are looking at only four tokens, one day a little. And one day a little, the four tokens, each of these four tokens are converted into a 768 dimensional vector. So the size of the matrix which enters the uh, processor block, it's actually 4 times 768. It's something like this. Okay, good. Now, if visualize this matrix, this is the matrix which enters the processor block. Now, before entering the processor block, there is one more step which happens, which is called as dropout. Dropout essentially means that we have now 4 multiplied by 768 parameters, right? You randomly turn off some elements to 0. This is a concept which comes from traditional machine learning, which helps the generalization performance. By generalization, I mean when we test our model on the validation set, it should generally give good results. So the simplest way to think about dropout is think about a group project. In a group project, let's say there are 4 people. There is always 1 or 2 people who don't do any work, right? So what would happen if 2 people who are doing most of the work suddenly don't come to work? The other people have no option but to pick up the slack and to work, right? It's similar to dropout. If some parameters in the neural network are lazy and they are not doing any work, if the other parameters who are doing the work are randomly turned off, the parameters have no option but to learn something. So that generally improves the generalization performance. All right. So this dropout actually does not change the size of the matrix. It still remains 4 by 768. And then we enter the processor block. Okay. So this is how the processor block looks like. This is also called as transformer block. The processor block, another name given to it is called as transformer block. And when we enter the processor block, we have a matrix whose size is 4 multiplied by 768. And typically, a processor block has 6 steps which are happening. It has this step called layer norm. It has this step called multi-head attention. It has this step called dropout. So let me mark them as 1, 2, 3. Then another layer norm 4, 5, and 6. Now, out of all of these steps, that step which is the brain of the language model is this multi-head latent attention. And once I explain this whole processor block to you, I am going to have a separate section where I explain this attention mechanism itself in detail. For now, as we are going through this flow, you can assume it as a black box. We'll come to it once I explain the whole transformer block. This attention mechanism deserves a special section on itself because it's very deep. But just remember that except for the attention mechanism, really everything else which comes over here has been studied in machine learning before. Layer norm is a normalization layer. I'm going to explain what it is. Dropout has also been done in ML before. Feed forward neural network is a traditional neural network. So all of this has been really done in machine learning before. The real advantage comes from this multi-head attention block. And I'm going to explain to you what that advantage is. Now, let's say we have entered this transformer block, right? And the size of our input is 4 multiplied by 768. The first step is applying a normalization layer. What layer normalization simply does is that it subtracts. So let's say if you have 768 dimensional vector, you take the mean and you take the variance. And then you subtract the mean from every value and you divide by the square root of variance. This will ensure that for all of these values, the effective mean becomes 0 and the variation becomes equal to 1. And you do this for every single vector. So you have 4 vectors of size 768 dimension, right? You first take a look at this vector. You subtract with the mean and divide by the square root of variance for all of these quantities. And you do that for all of these vectors. That eventually gives you vectors which have the same size. That won't change. But the mean of all, so the mean of the first vector will be 0, variance will be 1. For the second vector also, the mean of all the values will be 0, variance will be 1. For the third vector also, mean is 0, variance is 1. And for the fourth one also. Can someone tell me why do we do this? Why do we normalize? It does not seem to really change this, right? Change anything. Um, Why do we have normalization included at all? You can try to think from first principles. The main reason why we do normalization is because later we are going to do something called back propagation, which in which we are going to implement a procedure which is called as gradient descent. Now it happens, there are two issues which happen when we don't do normalization. First issue is that the training is not very stable. Some values may be large, some values may be very small. So normalization really makes gradient descent smoother. And second, it prevents the vanishing gradient problem. So without normalization, sometimes what happens is that when you back propagate to the first layer, gradients become zero, learning stagnates. Layer normalization has shown to prevent that. If you don't know what vanishing gradient is, don't worry. For now, just keep in mind that layer normalization is done so that training, when I say training, I mean we are going to tune all these parameters, right? Training just becomes smoother, training becomes stable. That's why we do this layer normalization step over here. That's the first step. Now we come to the second step, which is the masked multi-head attention. For now, for all of you, this is where the magic happens. That's all I will say right now. This is where magic happens. I'll come to what this step means. But the reason this step is so important is pay very careful attention to what I'm saying now. Until this point, there is no interaction between separate tokens, right? For example, this token effort, it has no clue which tokens surround it. It has no clue of the context of other tokens which are surrounding this token, right? It's just operating on its own. It got its position embedding vector, it got its token embedding vector, it got its input embedding vector. Even normalization is an operation where there is no interaction between neighbors. And this is a big problem because if you look at language modeling, unless every word knows all the other words surrounding it, how do you know about the context? Context is extremely important in language understanding, and that will not happen. We should, for every token should have information of all its other neighboring tokens. So ideally, let's say when you look at each token and it has this 768 dimensional vector, right? All of these values should have an influence of its neighbors. All of these values should be influenced by, okay, which neighbor is most important, which neighbor is least important, etc. And that kind of an understanding is extremely important because if you say Harry Potter casts a, and we want to predict the next token, if you just look at the word casts, it has no clue what context it's operating in, right? But if it knows its neighbors are Harry and Potter, it might have a better sense that the token which is going to come next is spell, like casts a magic spell. So the only place in the whole SLM architecture where this context building happens, where neighbors get to know about each other, is in this block called multi-head attention. And I'm going to explain at the end of this whole architecture block how this works. But for now, just remember that when each of these rows go through this multi-head attention layer, their output dimension does not remain same. It's still a 768 dimensional vector. But now, instead of being called as an input vector, we start calling each vector by a different name, and that name is context vector. Because now these 768 values also contain information of effort, moves, and you. So you might be thinking, how is this information added to this vector? That's the whole beauty of the attention mechanism. We are going to look at that because that's a whole separate thing in and of itself. But for now, just keep in mind that the multi-head attention layer, what it does is that it preserves the dimension, but context is now added. The vector for each word becomes more richer in terms of meaning. The vector for each word becomes more richer in terms of knowing its neighbors. This is where the true magic of language modeling actually happened. The reason Chat GPT is so good, the reason all these LLM tools which we use are so good is because of this attention block over here. Without this attention block being present, the answers which GPT gives us will not be very relevant. It needs to know the context. And here is where the context is actually captured. I'll come to this, but let's go through the rest of this architecture now. We have covered layer normalization, we have covered multi-head attention. Then there is dropout, and we have already seen what dropout means, right? Dropout, again, what it does, it randomly turns off certain elements and makes them zero to improve generalization performance. The size is again maintained, it's 768. That's no, the size does not change. After this point, there is one more block which is called as shortcut connection. I'll come to this once I explain the attention block, but essentially you can think of shortcut connection as uh, a connection which is added which gives an alternate path for the gradient to flow to prevent the vanishing gradient problem. So these shortcut connections essentially are just mechanisms to avoid or to make gradient training more stable. After this, there is another layer normalization block if you see. And this layer normalization does exactly the same thing what the first layer normalization does. So this layer normalization again makes sure that we take the mean, we subtract or we divide with the square root of variance. So again, we ensure that the mean and variance is stabilized. Because after we do all these operations, the mean and variance again might change, right? So we need to make sure that the mean is again 0, variance is brought back to 1. After this point, there is a very interesting layer which is called as a feed forward neural network. And this feed forward neural network has a very interesting architecture which looks something like this. So if you take a look at how many of you are familiar with what neural networks are? Familiar, right? So I'm going to assume that you have some basic level of familiarity with neural networks. If you are not familiar with neural networks, I would encourage you to just revise the concept after this class is over. But for now, I'm going to assume that you all know what a simple neural network is. So neural network essentially has an input layer, it has a hidden layer, and it's called as an output layer. A neural network which shows up in a language model architecture is often uh, in the form of an expansion contraction block. The reason it's called expansion contraction is because the input. Now remember, each input which goes to this neural network is of size 768. Remember, so I'm just going to look at one input for now, and we have these 768 values which are passed in. They go through this hidden layer, and the size of the hidden layer is 4 times 768. That's usually the convention followed since GPT-2 was released. So the size of this hidden layer is 4 times 768. And then there is a compression layer here once more. And the compression layer makes sure that the dimension is again retained back to 768. So we have an expansion layer where we go from 768 to 4 times 768. And then we have a compression layer, which again brings me back from 4 times 768 to 768. Right? And why do you think we have this expansion and contraction layer? What's the purpose of this neural network over here? Can someone try to think just from a purely intuitive perspective of neural networks? What's the purpose of this neural network over here? To increase parameter count. So remember, our goal is not to increase parameter count. Actually, it's the opposite. If possible, we want to decrease parameters as much as possible. So why do we have this neural network here? Find loss. So loss can be found even without this neural network, right? The main reason why neural networks actually exist is because they transport features into higher dimensions. And as is the case with deep learning, higher dimensions, when features are transported into a higher dimension, they go into a much richer space. And hence, it's actually, we can discover much more meaningful and richer representations in the underlying data in higher dimensions, which are not possible to do in lower dimensions. If you think what neural networks do, one perspective is that you can just think of neural networks as transforming data to a higher dimensional space and just hoping that things get better. And that's usually what happens in higher dimensional spaces. So the reason we expand and contract is because that allows a richer parameter exploration space. People have seen that if you remove this neural network layer completely, then the language model is not very good. The language model does not perform very well. It does not understand the context better. It does not give better representations or better meanings. But take a look at the number of parameters here. Actually, I'll come to parameters once I explain this architecture, but keep your mind aware regarding trainable parameters. This is the piece which contributes to a lot of trainable parameters, by the way. Why not have more than 768 dimensions? So we don't want more dimensions specifically. Ideally, we want more dimensions only when we are having this neural network layer, right? Because as you saw, if we have more dimensions from the start, that even increases the size of the token embedding matrix, that increases the size of position embedding matrix. So there it becomes difficult to increase dimensions since it cascades down into the whole architecture. Instead, it's much easier to have more dimensions here and then to project it back to a lower dimensional space. And then, so there is a question, basically till the attention layer, it learns the word position and relations, and later it learns patterns. That might be one way to think about it. After we come out of the attention, again, there is no relation with the neighbors. The attention mechanism is the only place where you capture contextual relationship. And when we come out and go to the neural network, even at the neural network level, every token is processed separately. But now every token is enriched with the context more. So this is the place where we try to capture more patterns in the underlying data. Once we come out of the neural network, remember again the size remains the same because 768 goes through 4 into 768 and comes back to 768. So for every token, the size still remains 768. So we started at 4 into 768, and by the time we are here, we are still at 4 into 768. Then after that, we apply one more layer of dropout. Which randomly masks certain elements. We have another layer of shortcut connection, which remember is just another path for the gradient to flow. And then after that, we come out of the transformer block. That's it. This is the whole transformer block. And to give you a quick recap, the transformer block starts with the input embeddings 4 into 768. We do layer normalization to stabilize the training. Then the place where the neighbors or the tokens get to know about their neighbors and where we encode context is the multi-head attention. Once we come out of the multi-head attention, the input embedding vectors are no longer called as input embedding vectors. They are called as context vectors because now they contain much more richer information about the neighbors. We apply dropout, then we apply shortcut connection. We apply one more layer norm to make sure the mean and variance again go to 0 and 1 respectively. And after that comes another very important layer, which is feed forward neural network. This just makes sure that we capture more patterns in the underlying data. Then we again have dropout and shortcut connections, and then we exit the transformer block. So remember that out of all of this processor, out of this entire processor architecture which we saw, the two places which are the most important are the multi-head attention and the feed-forward neural network. And these are the two places where all the advancements happen with respect to deep-seek latent attention, with respect to mixture of experts, etc. There is a question, shouldn't we again pass the embeddings to the multi-head attention after the NN step is over? Now remember that this architecture, this processor block does not end here. There is one more piece to the puzzle. And let me first take you through this journey. Okay, now stay with me over here. So I had made this kind of journey of a token through an LLM architecture. And the way it happens is that, again, first thing is every token is first isolated from its neighbors. It's assigned a token ID based on the vocabulary. It's assigned a token embedding vector. It's assigned a position embedding vector. And the addition of token embedding and position embedding is the input embedding. That's like a uniform, right, for every token. And now, since every token has a uniform, the token is finally ready to onboard the train to the transformer block. Every token goes through the transformer block, and the transformer block has all these different compartments. It has a normalization layer over here. Let me mark this with a different color. It has a normalization layer over here. It has the multi-head attention layer over here. It has the dropout layer over here. It has a skip connection, another normalization layer, another feed forward neural network, another dropout layer, and one more shortcut connection. This is what we have seen until now. The reason I've shown multi-head attention in a different color is just because it's where all the magic happens. But this is not the end of the story. This is just what happens in one transformer block, right? In a language model, there are multiple such transformer blocks. So I've zoomed out over here right now, and GPT-2, for example, had 12 such transformer blocks. So these input tokens go through the first transformer block. Then they go through another transformer block. Then they go through another. So they keep on going through multiple transformer blocks. And remember, each transformer block has its own attention layer, right? So over and over and over again, we try to find the context between neighbors. So if it gets missed in the first transformer block, we would capture it in the second, if not the third, etc. So this is the whole architecture, the processor block. I'm showing only one transformer over here, right? When I show the processor block, I'm just showing one transformer block. But in all the language models, there are multiple such transformer blocks which are aligned together. So here I'm showing 12, and this is when the tokens finally come out of the processor block. So the processor block is a step where a huge number of computations happen. Whatever computations happen in one transformer block, you would multiply it by 12, since you have 12 transformer blocks. And only then you come out. So here is where after the 12th transformer is done, you come out of the transformer block, the 12th transformer block. And the cool thing about transformers, the reason why they became so famous is that no matter how many transformer blocks you stack against each other, right, the dimensions of the input remain exactly the same. Remember, we started with a 4 by 768 input embedding here. And when we come out of these multiple transformer blocks, when we come out of these 12 transformer blocks, the dimension actually remains exactly the same. It's 4 multiplied by 768. That's why people like the transformer architecture so much. It just because it was so modular in nature. We can clearly stack different transformer blocks on top of each other. The reason we need so many transformer blocks is, of course, because one transformer block is not enough to capture the context and the patterns in the underlying data. We need multiple transformer blocks to be able to do that. And how many transformer blocks do we need? That's not known. That's a hyperparameter which needs to be decided during the pre-training process. For example, the larger models of GPT even had around 96 transformer blocks. Imagine those many number of computations. Now, if you take a closer look at this, you remember we started marking the trainable parameters with P. We had two places where we had marked P until now. The first is the token embedding matrix over here, and the second is the position embedding matrix over here. Now, in this whole transformer architecture, there are multiple places where we have trainable parameters. The first place is where we have the multi-head attention, and we are going to see that it has this query key and the value trainable parameters. One more place where there are trainable parameters is a feed-forward neural network. Can someone tell me how many trainable parameters are there in one such neural network? If you look at one neural network like this, how many trainable parameters does it have? So assume the same architecture. So the answer is not correct. 768 is not correct. 768 multiplied by 768 is also not correct. Essentially, if you take a look at this layer, this is my input layer of the neural network. This is my output layer. Let me see if someone has got the correct answer. Yeah, so the number of parameters here are 768 multiplied by 4 multiplied by 768. Because the hidden layer has these many number of parameters and the input layer has these many number of parameters, right? And I have a dense network going on over here. So actually Pawan has given the correct answer here. The correct answer is 768 multiplied by 4 by 768. These are the number of trainable parameters in the expansion layer, and in the contraction layer, we have similar number of trainable parameters. So the total number of trainable parameters is 768 multiplied by 4 multiplied by 768 multiplied by 2, right? And so if I calculate it over here, it will be 768 multiplied by 4 multiplied by 768 multiplied by 2. And that would be around, if you take a look at the number of parameters here, that's around 4 million parameters. So there is a question, why is it 4 times 768? Because that's the number of parameters which we have in the hidden layer, right? If you look here, every single weight is connected to every single weight here. So there are 4 into 768 neurons in the hidden layer. There are 768 neurons here. So the number of parameters here will be 4 into 768 multiplied by 768. So essentially, if you had a neural network like this, just think about this, right? If you had a neural network like this, how many parameters does it have? It has 2 multiplied by 2, right? It has 4 parameters. Sorry, it has 2 over here, and 2. So it's 2 plus 2. That is why it's the exact same thing what I'm doing over here. In the expansion layer, the number of parameters which are there are 768 multiplied by 4 times 768. And in the contraction layer, it's 768 multiplied by 4 times 768. So I'm assuming bias term is not here for the sake of simplicity. So forget the bias, just keep into account the weights. So the number of parameters from one such neural network is 4 million. And remember, we have 12 transformer blocks, right? So if you multiply, so this is around 4 million. And we have 12 such transformer blocks. And each transformer block has a multi-head attention. And each multi-head attention has a neural network within it. So it's like the total number of parameters here are actually 4 million multiplied by 12, which is around 48 million parameters. Or let's say around 40 million parameters here. So this is another place which actually increases the total number of parameters. If you are not able to understand this, it means your basic concepts about neural network are not very clear. Because for a fully connected neural network, the number of trainable parameters are equal to the number of neurons in the input layer multiplied by the number of neurons in the hidden layer, right? And what are the number of neurons in the hidden layer? 4 multiplied by 768. What are the number of neurons in the input layer? It's 768. So the number of trainable parameters is 768 multiplied by 4 by 768 in the expansion layer and the same number of parameters in the contraction layer. So you add them together and then you have to multiply it with 12. So that gives rise to around 40 million total parameters. So this is another parameter sink. The places which have more number of parameters are called as parameter sink. So now you can start imagining, why do people talk about language model in terms of millions and billions of parameters, right? Is because of all of these places in the LLM architecture which actually need these many number of parameters. Uh, okay, so has everyone understood until now? Can you mention in the chat? I have not gone through the multi-head attention, but apart from this, has everyone understood the entire flow of the architecture? By now, you should be able to appreciate how complex this architecture is, but at the same time, it retains the dimensions when we come out of this processor block. Okay, so now we are going to take a very small break of around 3 to 4 minutes, because after the break I am actually going to explain to you about the attention mechanism. Uh, this is going to be a separate section in and of itself. And in this section, we are actually going to try to understand what happens in this step. I mentioned to you one step, right? This step, which I did not explain, I mentioned to you this step as a black box. Now we are going to visually understand what is going to happen in the attention mechanism. For this part also, you need to be very focused because it's the brain of the language model, as I mentioned. So now we are going to enter the brain of the language model really. And this is one of the major innovations. So all of you should be uh, focused and all of you need to be attentive here. Yeah, so let me come back after 2 to 3 minutes. All of you can also take a break, drink some water so that you are fresh for the next section. Thanks. All right, so let's now continue with the next part. Before that, there are some questions in the chat I would like to address. Remember that when these transformer blocks are stacked together, right? After you come out of the first transformer block, the dimension remains 768. The dimension always remains 768 after you come out of one transformer block and go to the next transformer block. That's why stacking these transformer blocks together is so easy. Okay, now let me come to the attention mechanism. And I hope everyone is here because this is the part which is very easy and not very easy. I would say once you understand it, it becomes easy. Once you understand the mathematical notations and the matrix multiplications which happen. But for that, you need to really be focused here. Okay. So let's see what's going on. Our starting point is this point where we have just finished this normalization. We have finished this normalization and we are now entering the multi-head attention block. Now we are going to see exactly the sequence of steps which happen in the attention mechanism. Remember what I told you in the attention mechanism, words get to know about their context, right? So we are going to look at 5 such words. The next day is bright. And you can think of these as currently 8-dimensional vectors. In the example which we saw, it was 768 dimensions, but I've chosen less dimensions here so that I can explain it properly. And remember that currently we have just come out of the normalization block, and every word has its own embedding. And until now, no word has actually have any idea about the words which are surrounding it. In the attention mechanism, there are 3 weight matrices which are defined. The first weight matrix is called as the query matrix. The second weight matrix is called as the key matrix. And the third weight matrix is called as the value matrix. And remember, these weight matrices are trainable matrices, which means the parameters of these matrices WQ, WK, and WV are not known before to us. We don't know this. So you must be thinking, why are these weight matrices introduced, right? So humans have done this for a long period of time, right? Humans figured out that we need to find out the context. We need to find out how tokens relate to each other, but we have no clue how to do this. So let's offload this to a deep learning model. Let's create trainable weight matrices and let's hope that when these trainable weight matrices are optimized, we do capture some contextual relationship. So what's done is that this X matrix, it's 5,8 right now, right? It has 5 tokens and it's an 8-dimensional vector. This WQ, WK, and WV, these are trainable weight matrices, and its first dimension has to be equal to the embedding dimension. And its last dimension, it can be anything, but usually it's taken as the embedding dimension itself. I'm choosing it as 4 for now. So you multiply X with WQ, WK, and WV, and then you get a query vector matrix, which is a 5 by 4 matrix. You get a key vector matrix, which is a 5 by 4 matrix, and you get a value vector matrix, which is a 5 by 4 matrix. To get the context vector, so these are the input vectors, and from this we have to get context vectors, right? To get the context vectors, we only deal with the query vectors, the key vectors, and the value vectors. After this point onwards, the input matrix becomes irrelevant. We only take a look at the query vectors, the key vectors, and the value vectors. So if the input looks something like this, we multiply with WQ, WK, and WV, and you get this Q matrix, you get this K matrix, and you get the V matrix. That's the query matrix, key matrix, and the value matrix. The values in WQ, WK, and WV are not the same. All are initialized randomly. And after this point is where all the magic actually starts to happen, right? So now what I want to do is that I have this query and I have the keys vector, right? And I want to get how much attention should exist between different tokens. So let's say the next day is bright, right? These are all the tokens. So what I want to now see is that if I focus on one word, which is next, let's call it the query. And if I focus on all the other words, let us call these as keys. So I have a query and I have these keys. What I'm going to do now is that I'm going to find the attention score between these query vectors and the keys vectors. So the way this is done is that you want to find the attention score between this query and this key. So that will be alpha 2, 1. I want to find the attention score between this query and this key. So alpha 2, 2. I want to find attention score between this query, this key, alpha 2, 3, alpha 2, 4, and alpha 2, 5. These attention scores will give me the importance which every query should pay to all of these keys. And once you have the query matrix and the keys matrix, it's easy to find the attention scores, right? This is the query matrix, which is 5 by 4 matrix. So I just look at the second row. The second row gives me the query vector for next. And then to get the attention scores, so to get the attention score between next and the, I just multiply this row with the first column of keys transpose. To get the attention score between next and next, I multiply this row with the second column. To get the attention score between next and day, I multiply this row with the third column, etc. So the way we get the attention scores from the queries and the keys matrix is we multiply queries with keys transpose. So queries is 5 by 4 and keys transpose is 4 by 5. So when you multiply queries with keys transpose, you get the attention scores matrix, which is a 5 by 5 matrix. And this matrix is extremely crucial because it conveys a very important thing. If you look at every row of this matrix, it means something now. When I look at the second row, I know that the second row gives me when I look at the word day, when I look at the word next, the second row kind of signifies how much attention should I pay to all the other tokens when I'm looking at next. So this 0.1 value indicates the attention between next and the. This 1.8 value indicates the attention between next and next. 0.6 indicates the attention between next and day. 0.1 indicates the attention between next and is. And this 0.1 indicates the attention between next and bright. Similarly, every single row of this attention scores matrix can be interpreted. If you look at any random value, if you look at this value conveys the attention score between day and is. Because if you see, the next day is bright, right? And on the row also, the next day is bright. So this value conveys the attention score between day and is. All these attention score values currently have meaning. And these values are random right now. We have initialized all the weight matrices randomly. We hope that when the language model is trained, these values actually make sense. So the first step is to multiply the queries with the keys transpose and to get the attention scores matrix. But the issue here is that this is a very weird matrix, right? If I'm going to look at if I'm going to look at the next, I want to make some predictions, like if you're looking at next as a query, pay 10% attention to the, pay 30% attention to next, pay 20% attention to day, pay 10% attention to is, and pay the remaining, which is pay 30% attention to bright. I want the attention scores so that for every row, the attention scores will add up to 1. Why do I want the attention scores to add up to 1? I want the attention scores to add up to 1 because I want them to be interpretable. I want to make statements such as this. If the attention scores add up to 1, I can easily say that for the given query, next you pay 30% attention to bright, etc. So the next step which is done to these attention scores is that we are going to apply softmax. Before applying softmax, the attention scores are first scaled with the square root of the keys dimension. And then we apply softmax. How many of you are aware of what softmax is, by the way? So let me quickly explain what softmax is. If you have a row, right? If you have a matrix of values, something like this, or if you have a vector of values, and if you want all these vectors sum up to 1, the softmax operation, what it does is that it takes the exponent and it divides each with the sum of the exponent. So the first value will be e raised to 1 divided by e raised to 1 plus e raised to 3 plus e raised to 4 plus e raised to 5. The second value will be e raised to 3 divided by the summation. The third value will be e raised to 4 divided by the summation, and the fourth value will be e raised to 5 divided by summation. Now, if you carefully take a look at all these values, you'll see that they add up to 1. That's very nice. And since it's exponential operation, they are always positive. So these values can be interpreted as probabilities when you apply the softmax function. So now when I scale the attention scores matrix and I apply the softmax, the matrix which we get is called as attention weights. That's the difference between attention scores and attention weights. If you only look at attention scores, the row does not typically add up to 1. But attention weights, if you see, since we have applied softmax, the rows will add up to 1. So now I can look at each row. So if I look at the second row, I know that when you're looking at next as the query, I need to pay 50% attention to next. I need to pay 20% attention to day. I need to pay 10% attention to all these other tokens. So suddenly it becomes much more interpretable matrix now. Instead of having these values which don't add up to 1, by an appropriate scaling procedure, I make sure that each row sums up to 1. You may be wondering, why are we scaling with the square root of keys dimension, right? So there is one reason for it. The reason is that the queries into keys transpose, when you are doing queries into keys transpose, and if you don't divide with the square root of the keys dimension, the variance of this matrix goes on increasing as dimension increases. That's not what we want when we get the attention scores. That's why we divide with the square root of the keys dimension. So it makes sure the variance of every row essentially stays very close to 1 and stabilizes training. Both of these questions are very frequently asked in LLM interviews. What's the difference between attention scores and attention weights? And second question is, why do we scale with the square root of the keys dimension? You need to be aware of both of these. The reason we scale with square root of keys dimension is to make sure that the variance of this queries multiplies with the keys matrix does not become too high, which stabilizes training. And the reason we apply softmax is we want every row to sum up to 1 so that we can make interpretable statements about which token is important as we look at other tokens. However, this is not the end of the story. What I want to do after, you remember the goal which we started with was that every input vector needs to be converted into a context vector. I have got these attention weights now, but those are not enough. I need to use these attention weights to convert every input vector into a context vector. And the way that is done is that attention weights is multiplied with this value matrix, and then we get the context vector matrix. Let me explain actually what happens over here. So here is my attention weights now, right? And here is my values matrix. Okay. Now let's say I want to pay very careful attention to this part, please. If I want to find the context vector for next, these are just the attention weights, right? How do I find the context vector for next? Attention weight tells me how much importance I need to give to each token. So I need to give 10% importance to I need to give 50% importance to next. I need to give 20% importance to day. I need to give 10% importance to is, and I need to give 10% importance to bride. This is exactly how the context vector is calculated. The way it's calculated is you multiply the vector with 0.1. You multiply the next vector with 0.5. You multiply the day vector with 0.2. You multiply the is vector with 0.1. And you multiply the bright vector with 0.1. Essentially, it's a weighted summation of the values vectors. And that gives you the context vector for next. So now for next, you know that 10% importance is given to the etc. So the way it's calculated is like this. You have let me draw it again. The next day is bright. Okay. Before coming to the attention matrix, this next was just an input embedding vector. But now what we are doing is that I know that I need to pay 50% attention to next. I need to pay 10% or 20% attention to day. And I need to pay 10% attention to all these remainings. That's where I capture information about neighbors. And then I will scale all of these vectors with these values. And the resulting vector which comes out is the context vector for next. And the reason we say that this vector is much more richer than the input embedding vector is because it actually is the weighted summation of all of these vectors. So the context vector for next not only contains information about the input embedding for next, but its neighbors also. And these neighbors are scaled accordingly based on how much weight needs to be given to each surrounding neighbor. That's the whole idea of uh, context vector, converting input vectors to context vectors. Let me explain this once again. So let's see. Let's go from the top here, because this part is very important. I hope every one of you understood till the attention scores part, right? Can you mention yes in the chat if you have understood till the attention scores part? I'll explain the next part once more. Okay, the main key lies what happens next, right? So when you get the attention scores, you do two things after this point actually. You scale or you divide with the square root of keys dimension. Uh, why do we divide with the square root of keys dimension? It's just a trick which comes from statistics. Because when you directly take queries multiplied with the keys transpose, uh, and when you look at the rows, the variance of that matrix actually goes on increasing as the dimension increases. So if you scale by square root of this, it just means you divide all of these values with the square root. So the keys dimension, which means the number of columns in the keys matrix, right? You just divide with the square root of that. And that makes sure that training becomes stable. So it makes sure that the variance of the attention scores matrix always lies close to 1. And during back propagation, it does not lead to any weird issues for us. So that's scale by the square root of keys dimension. And after that point, we are going to apply softmax. So for every row, what we are going to do is that we are going to take the exponent of each value and we are going to divide by the summation of exponents, just like how I showed over here. For every row, we are going to do the same thing. That will make sure that every row has positive values and every row sums up to 1. So that I can think of each value in each row as a probability. So if I look at the second row, right, it gives me the attention weight for next. Now, when I look at the second row, I know that I need to give 10% weightage to the 50% weightage to next, 20% weightage to day, 10% weightage to is, and final 10% weightage to bright. So this is where we get the attention weights. That's the difference between attention scores and attention weights. There are two major differences. You scale by the square root of keys and you apply the softmax. But until now, you have only got how much importance I need to give to tokens. I have not got the context vector. The goal is to transform the input vector to context vector. And the way we do it is that we look at the values vectors. For every token, the next day is bright, I have this value vector, right? So what I will do is that if I'm looking at this second row, which is next, I know how much importance needs to be given to each value vector. So I'm just going to multiply that corresponding value vector with how much importance is going to be given to that vector. So for example, this value vector will be multiplied with 0.1. So this row will be multiplied with 0.1. Next, this entire row will be multiplied with 0.5. Day, this entire row will be multiplied with 0.2. Is, this entire row will be multiplied with 0.1. And bright, it means this entire row will again be multiplied with 0.1. And then I'll add all of it together. So in a sense, what we are doing is the input embedding vectors where the next day is bright, right? Shown in the red colors over here. They had no clue about what their neighbors had. But now if you look at next, the way I calculate its context vector is that I have relative importance need to be given to the value vectors of each of these, and I take a weighted sum. And that's how I get this context vector for next. It's much more richer than the input embedding vector because now it contains information about neighbors. It contains information about how much attention needs to be paid to the neighbors. I hope you understand the intuition behind why the context vectors are much more richer than the input embedding vectors. This kind of transformation which I showed you right now, right? Going from the queries, going to queries multiplied by the keys transpose, going to the attention scores, going to the attention weights, and then ultimately getting these context vectors. That is exactly what happens in this step. So when I say masked multi-head attention, these steps are what is happening. So you may be now thinking what is masked and what is multi-head. There are two reasons why it's called masked and multi-head, which I will try to explain now. So the first reason why it's called multi-head attention is that usually now what we saw, it's a single head attention mechanism. In multi-head attention mechanism, we assemble multiple different attention heads. So I don't have too much time to explain this right now, but basically what happens is that instead of looking at a single uh, trainable query vector, key vector, and the value vector, we look at different heads. So we look at multiple heads of the key trainable key query vector, trainable key vector, and the value vector. That's where the term multi-head attention comes from. And the reason we need multiple heads is because if you just take a single head, you can capture only one perspective in a language. For example, take a look at this sentence, right? The artist painted the portrait of a woman with a brush. Now, this can be either interpreted like this, which means the artist is the one who is doing the painting. Uh, the artist painted the portrait of a woman with a brush. Or the second, the artist painted the portrait of a woman with a brush. So the first is painting a woman with a brush, and second is painting of a woman with a brush. Different perspectives, right? If you just have single head, you cannot capture all of these perspectives. And that's why we have multi-head attention mechanism. And the reason why it's called masked, it's because when you look at these attention scores, yeah, if you look at the attention scores right now, or let me show it to you over here. If you look at these attention scores, it's kind of like, let me, so the next day is bright and the next day is bright. Okay. And you have attention scores here, right? You have all of these attention scores. But this is kind of like cheating, right? Because when you're looking at one token, you actually have no clue what is going to come ahead of it. You only know what has come before it. So technically, we don't know all of these attention scores, because when I look at I have no clue what is going to come after it. So I mask out these attention scores. I put them to 0 because I don't know these. All of the attention scores which I've marked in orange color right now, I put them to 0 because I cannot look into the future. Uh, I cannot look into the future. So when I'm looking at a particular token, let's say is or day, I only know that next and day come before it. Next and the come before it. I should not know what comes after it. So there is no point in finding the attention scores between what comes after the day. Because remember, we are training the LLM to predict the next token. So we should not peek into the future really. So all of these attention scores are set to 0. This is called as masking. So the attention, when I showed you the attention weights, after this a masking procedure is done when all the elements above the diagonal are actually put to 0. And the reason though elements above the diagonal are put to 0 is because we cannot peek into the future. That's where the term multi and masked actually come into the picture. So the reason why this is called as masked multi-head attention, the term mask comes from the fact that we cannot peek into the future. And the term multi-head comes from the fact that we have multiple attention heads to capture multiple perspectives. But as long as you have understood what I explained over here, it kind of drives home the point of how input vectors can be converted into context vectors. And remember here, the D out of these trainable matrices I chose is equal to 4. So the context vectors here had a dimension of equal to 4, right? But usually people choose D out to be equal to D in. So if D in is equal to 768, we choose D out also to be equal to 768. that makes sure that the context vector size is the same as the input vector size. Now, remember that all of these vectors are randomly initialized. WQ, WK, WE, these are trainable parameters. We don't know them beforehand. All of those are randomly initialized. And through the back propagation procedure, we'll slowly try to find the best values of these parameters. So if you look at how complex this mechanism is, if you thought this was complex, in each multi-head attention block, so if you look at these 12 transformer blocks over here, and if you zoom into each multi-head attention block, within each multi-head attention block, there is all of this happening, which I just showed you right now. The queries, keys, and values. And this kind of a procedure, the queries, keys, and the values, this is happening in all these other multi-head attention blocks also. So number of transformer blocks is one parameter. Another parameter is number of heads which you have to choose in this attention block. You can have 6 heads, you can have 7 heads, etc. You can have 12 heads. The more the number of heads, the more perspectives you aim to capture, but it also increases the number of parameters. Does all 12 transformer blocks execute parallelly? So we can do parallel computations as well to speed up the operations for sure. Now, if you have understood this entire architecture of the processor block, DeepSeek and all these other papers which came after it, they actually had innovations in this part and this part, which is mixture of experts over here and multi-head latent attention over here. But don't worry about these right now. For now, your main purpose should be able to understand the SLM model architecture itself. Has everyone understood this attention part intuitively? So especially this part of how the multi-head attention happens. There is so much more digging which you can do after this point. I've only explained it to a point where you will understand it intuitively. So in this point, now you should be able to appreciate why we say that an attention mechanism captures information about its neighbors. That is actually contained in the attention scores. And now you should be able to appreciate why I mentioned that context vectors are much more richer compared to input vectors. Okay. So now that you have understood the attention block, we now understand the entire transformer block of the LLM architecture. So the thing is, once you come out of this processor block, if you see over here, once you come out of the processor block, we have still not predicted the next tokens, right? The goal when we started this lecture was, how am I going to take my input tokens and predict the next tokens? So currently we have not predicted these next 4 tokens. This prediction happens in the output block. So this is the last part of today's lecture. Let's see how the output block actually proceeds. Once we come out of the transformer block, we have this 4 by 768 dimensional matrix. Its size has remained the same. That's nice. And then we again apply layer normalization once more to make sure the mean and variance is equal to 0 and 1 respectively. This layer normalization layer is mentioned over here. Let me bring this architecture over here so that I don't have to scroll up again every single time. Yeah, this layer normalization. Yeah, if you look at this, we are now at the output block. And in the output block, we have one more layer normalization. This one, which I just showed you right now. And then the final step of the output block is something which is called as the attention head. Now, please pay very careful attention here, because here is where we will actually try to understand how do we do the next token prediction. So until this point, we are at a stage where the size remains the same, 4 multiplied by 768, but we are nowhere close to predicting the next token. To predict the next token, remember that we have a vocabulary of 50257, right? So we need to somehow look into this vocabulary and predict what the next token is going to be. So the first step is that we need to transform this matrix from this 768 to my vocabulary size. I need to transform the matrix from an embedding size to the vocabulary size. So what I do at this stage is that I multiply this matrix, which is 4 multiplied by 768. I multiply it with the neural network layer, whose size is equal to embedding dimension multiplied with the vocabulary size. And that gives me a matrix such as this, whose size is equal to 4 multiplied by 50257. Now remember when I mentioned to you at the start why word-based tokenization is not good. Word-based tokenization is not good because the vocabulary size really increases the number of parameters. This neural network size is also governed by the vocabulary size. So this neural network is called as an output head, which projects the tokens from an embedding dimension to the dimension of the vocabulary space. So now I have a matrix which is 4, 50257. For each token here, I have 50257 values. For the first token, I have 50257. For the second token, I have 50257. For the third, I have 50257. And the fourth, I have 50257. Uh, and now what we are going to do after this point is going to be very simple. We are going to just apply softmax and convert every row to a row of probabilities. And we are going to look at that token ID, which corresponds to the maximum probability. So if we look at the first row and the token ID number 5000 is the maximum probability, we go to our vocabulary, and we look for the token which is named as 5000. So that gives me the output. So let's say the output, that token is the. Then I look at my second token, which is effort. I look at that index, which has the maximum probability. I again go to my vocabulary and decode that index. Let's say that output is flag. Whatever. Then I go to moves. I look at the token. I look at that index, which has the maximum probability. And that gives me the prediction for moves. Similarly, I look at U and I look at that token which has the maximum probability, and that gives me the next prediction for you. We started this lecture with an example, one day a little, right? If you remember, we started this lecture with this example, one day a little. So what happens at this final output head is something as follows. One day a little, right? In the final output head, for every token, we have a vector with the vocabulary size. We look at the index with the highest probability and we decode it based on the vocabulary. So we get the output for one, we get the output for day, we get the output for and we get the output for little. And we already have the targets. The target is day, a little girl for our next token prediction tasks. And then we will just compare the loss between the output and the target. We'll see how to compute the loss in the next lecture. That's not the main purpose of this lecture. The main purpose of this lecture is to understand how exactly we get the next token predictions from our model, right? So every effort moves you. Now we have 50257 row vector for each token. We just look at the index with the maximum probability and we predict the next token from our model. Of course, these predictions will be very bad initially because we have initialized all the parameters randomly. And we have later we will compare it with the actual ground truth values. So the output, if you see the output block, it's actually pretty simple. The output layer just consists of a matrix which has the size equal to the embedding dimension multiplied by the vocab size. So essentially it's this. So I multiply it with this neural network with this size and I project it back to my vocabulary space. So if you want to imagine what a vocabulary looks like, it's just a dictionary. It's a key value pair basically. You have token IDs and you have so you have these token IDs and then you have tokens corresponding to every token ID. So you can encode and you can decode very easily. Did everyone understand this part about the output head? Can you mention in the chat? This output head is actually quite straightforward once you understand the attention mechanism and the context vector matrix. So this is how the entire architecture is structured. You have the data processing layer, you have the data layer, you have the processing layer, and you have the output layer. So right now I just showed you how four tokens can enter 4 token IDs can enter this input processing block, and they go through this entire journey. And what comes out is the next token prediction for all of these 4 tokens, which we are going to compare with the actual next tokens, and that gives us the loss. So what I just showed you for these 4 tokens is the exact same procedure which is going to happen for this entire batch. So right now I showed you how next 4 tokens are predicted for these 4. Similarly, it will be predicted for these 4, these 4, and these 4. And we'll get all the predictions from one batch. We'll compute the loss from one batch. We'll compute the loss from one entire batch, and then we'll do the back propagation. That's how we are going to update our parameters. What does it mean when someone says Llama has a context size of 200K? So currently we have context size of 1024, right? In the examples which we just saw. When Llama has a context size of 200K, it just means that the amount of tokens. So if you look at this, right, each input batch, every sequence now has only 4 tokens. But if you have 1024 tokens or 200,000 tokens, the number of tokens which come in one input sequence will be that high. So 50257 is the vocabulary size when we create the vocabulary for GPT-2. So loss function and back propagation I'm going to explain in the next lecture. Today's lecture is mostly about next token prediction task. So in today's lecture, I tried my best to condense a lot of information related to the LLM architecture. And this lecture is, as I mentioned at the start, it's the brain of a small language model, really. So if you felt this lecture was a bit fast or there are some portions which you did not understand, you will need to go back and revise this. You will need to go back and look at this lecture once more. If you have if you're completely unfamiliar with this topic, you definitely will need to revise this lecture 1 or 2 more times. But if you are familiar with this topic, then many of the things you can use it as a revision for you. But I've intended this lecture to convey the intuition as easily as possible and at the same time without confusing all of you too much. So we are almost at the end of time. So what I want to do in the last 5 to 10 minutes is just go through code, right? So we won't be running all the code so far. What we have done is that we have already ran step number 1, we have ran step number 2, and we have ran step number 3. The only thing which I want to go through right now is the SLM architecture, and I'm going to share this code file with all of you. We'll go through this again in the next lecture as well. But now, since we are almost running out of time, let us actually uh, now we should be able to see and relate to everything what we have learned so far on the whiteboard. So if you look at step number 4, which is defining the LLM or SLM model architecture, it is this one big block of code and which you might get intimidated by. But once you understand the full lecture, right, it's actually pretty straightforward. So start at this block. This block here is the transformer block. You have a normalization layer, you have a self-attention layer, you have a normalization layer, and you have a feed-forward neural network along with uh, shortcut connections. This is exactly the same architecture as we have been seeing on the whiteboard schematic. This same architecture of the transformer block, which we have been seeing here, that's replicated in this class, which is called as block. Now we have defined separate classes for each of these. MLP, which is the multi-layer perceptron, that's the feed-forward neural network. Then layer normalization, causal self-attention, and layer normalization. So if you scroll above, you will see the feed-forward neural network, which we saw, the expansion block and the contraction block. If you scroll further above, you will see a block for causal self-attention. This actually includes the query, key, and value computation, which we just saw. So converting queries, keys, values into a context vector. And if you scroll further above, you will see the layer normalization block, which is essentially subtracting the mean and dividing with the square root of variance. And then you just divide, you define a GPT architecture where you initially start with the token embeddings. You start with the position embeddings. You add the token embeddings with the position embeddings. You go through the transformer blocks. There will be 12 such transformer blocks. And then you go through the output head. That's it. So these 5 lines of code which have been written here are essentially the data processing block. That's the token embedding, position embedding, adding the token and position embedding, then going through these 12 transformer blocks. So see, this loop essentially loops over the multiple transformers. As I showed you over here, we have 12 transformer blocks, right? So we go over a loop. We go over a loop through all of these transformer blocks. And then we come up with the output block. So after this class is done, I really encourage all of you to also go through this code block once more. We'll see it once more in the next lecture. And our next lecture is going to be on Saturday, which is at 2 p.m. IST next week. So before the next lecture, I would encourage you all to do two things. First, revise what all we have covered so far. For the people registered for the pro plan, even the lecture notes are available on your dashboard. Second thing which you should be doing is that you should have the Google Colab Pro, because we will be in the next lecture. What we'll be doing is that we'll be defining the loss function, and we'll be setting up the SLM training pipeline and pre-training the SLM. So you need to make sure that you are on Google Colab Pro, so that when you click on change run type, you should see this A100 GPU. Right now, I also cannot see it, which means I'm probably out of credits. But make sure you have that. Otherwise, you won't be able to run inference on your machine. And please revise whatever we have covered so far. This was a pretty intensive and a heavy lecture, but the recording will be available on the dashboard for everyone who has registered. So you will be able to see the recordings as well. You don't need Google Colab Pro Plus. Even Google Colab Pro will be available. We are right now not putting these videos on YouTube. We are only putting it on dashboard so that people who have registered can see it. So if you cannot see the dashboard, you should see it over here. If you have either enrolled for the free plan or pro plan, you should be able to see a dashboard. If you have to build, so currently what we are assembling, that stays the same across LLM as well as SLM. The only change which is there is in our data set. In SLM, we have identified a very specific data set. So we'll see that during pre-training, since our data set is small and specific, it becomes easier to train the SLM. If you have billions and billions of parameters, the training pipeline will be just a bit harder. Right now, we are definitely going for an SLM because the number of parameters will stay the small. Oh, so we have next lecture on 16th of August, which is basically on Saturday. And the lecture after that will be on 17th of August, which will be on Sunday. So to train this SLM, if you have A100 GPU, it will take around 1 to 2 hours. If you have T4 GPU, it might take 8 to 9 hours, and then the computer actually keeps crashing. If anyone wants to actually deploy an SLM in enterprise, it's high time that you upgrade to GPUs. You cannot keep training on T4 GPUs if you want enterprise level applications. Thanks everyone. So I look forward to now seeing you in the next lecture on next Saturday. Please keep revising this content. I'm sure that once you revise it, you'll feel very confident about language modeling in general. Thanks a lot. I hope you found the lecture intuitive and engaging also. We will now meet again on next Saturday at 2 p.m. IST. These lectures are becoming a bit long than I expected, but I had originally planned 5 hours, but it's becoming much more than that. No problem. So we have to still do the loss function pre-training and inference. We'll try to cover it all on next Saturday and Sunday. Thanks everyone, and we'll see you in the next lecture. Bye.